Good afternoon, everybody. This is Group B. My name is Thomas Price, and with me we have Lake Miller, Rusty Horry, and Stephen Yan. Our presentation today is going to be on solar panel fault detection. Alrighty, so before we actually hop into our project and explain how it actually works, we just like to take a moment to define a few key terms. So the first of the terms being photovoltaic, you'll see shorthand is PV. This abbreviation pops up pretty commonly throughout our presentation today. So if you notice, the remainder of the key terms below actually contain the abbreviation PV inside of the term. So photovoltaic, what is that? That's actually the process of converting light into electricity. The next term is a PV module, the entire device that absorbs and transforms the light into electricity. So the PV module is pretty much the device that encompasses the photovoltaic process. The next term is a PV panel. This is composed of one or more PV modules and an enclosure. So whenever you're thinking of a PV panel, if you imagine a solar panel, you're exactly correct. So a solar panel basically contains at least one PV module, but more times than not, it contains multiple PV modules on it. The next term is a PV array, a matrix of interconnected individual PV modules that produces electricity as one cohesive unit. So if you think about a solar farm, that's what a PV array is. So all of these solar panels collect electricity and they send it to one common point before sending it out to the main electrical grid. It should also be noted that PV is often dropped when discussing these components within the industry. It's just a common practice. So you'll notice throughout the presentation, we're going to say things like module and panel without the abbreviation PV beforehand. Just understand that that is common practice and be on the lookout for that. The previous slide was responsible for defining some key terms and describing them using words. This slide is going to help you kind of put an image to the description. The previous slide was responsible for defining some key terms and describing them using words. This slide is going to help you kind of put an image to the description. So if you look at the upper left-hand picture first, that is a photovoltaic cell. Photovoltaic cells are responsible for the actual absorption of the sunlight. If you look at the upper right-hand picture, that is a PV module. If you look, a PV module is composed of multiple PV cells. The next picture is going to be the bottom left. That is a PV panel. A PV panel is composed of multiple PV modules. And finally, on the bottom right, PV panel, modules. And finally, on the bottom right, we have a PV array. And a PV array is composed of multiple PV panels arranged in either a grid or a matrix form. Now that we've gone over some general background knowledge and information, we can actually get into how our project works and what our project is actually trying to accomplish. So our objective is to create an alarm and annunciation system to detect damaged or inefficient PV panels within a PV array. So how will our project actually function? As we discussed before, the main goal of our project was to identify underperforming PV panels within a PV array. That way so we can pinpoint its exact location and cut down on service times. Some of the possible reasons why our alarm could trip could be due to damaged PV cells or modules, whether that comes from the environmental conditions, whether it's man-made from landscaping around the solar farms. There's a multitude of reasons this could happen. Another possibility is the angle of the PV panel is skewed. So this actually happens whenever the panel is not at its optimized angle to absorb the most sunlight throughout the day. One other reason could be the actual lens itself is dirty. So if there's a lot of dust floating through the air and a lot of dust accumulates on the surface of these lenses, it can actually cloud up the lens and not allow for the optimal amount of sunlight to pass through, which could cause the PV panel to underperform compared to its peers.
Using this program, a technician would more readily be able to troubleshoot or identify faults within a solar field. To start, we can look at a standard solar field layout as shown to the right. This solar field layout is known as a block solar field layout, and it is ideal for maintenance and upkeep because everything is easy to access and in order. However, the block layout has a few downfalls. It consumes space and does not mesh well with the environment or local ecosystem. An idea for a less environmentally intrusive solar field would be to disperse the solar panels over an already used space. For an example, we can take these solar panels and spread them across the roofs of multiple houses, various areas of an airfield, or even agricultural structures and equipment. In these examples, um, the equipment or solar panels would not easily be accessed, and they would have to share a common power inverter. With a dispersed solar field, a fault monitoring program like the one we were trying to design would have a much bigger role, as degradation of the individual panels would be more difficult to monitor. How are we going to make this program? Well, we can start by creating a mock solar field. To get the basis, we need to represent each panel in an array. For our mock solar field, we have chosen a 20 by 20 array, which equates to 400 individual solar panels. Here, we will set the output of each panel through random number generation. Based on our research of common panels used in the solar fields, we have selected our solar panels to be 400 watt capable. For a model, we have been using the Old Plank Road solar facility on the west side of Jacksonville. It's interesting to note that this solar facility only uses 2 power inverters and produces around 5,000 megawatts per hour of energy. We are working on taking output data from the Old Plank Road solar facility and using it as input. Rustam will cover this in more detail. Next, we will sort the program array into set ranges that will correspond to a specific color. For colors, we have chosen green, yellow, and red. Green will represent a good solar panel at a 250 to 400 watt range. Yellow will be a degraded or dirty solar panel at 75 to 250 watts. Red will represent a bad or faulty solar panel at 0 to 75 watts. These colors will be displayed on a 20 by 20 square grid plot, where the square itself will represent panel location and the color will represent power.
We tasked ourselves to implement a way to take energy data collected by JEA and quantify these measured variables to function as parameters during actual solar harvesting. JEA harvests solar energy on residential and commercial properties. They also have solar farm facilities in various locations around Jacksonville. Each farm ranges in acreage and number of photovoltaic panels. The solar array can consist of approximately 20 to 25 of these panels. The 8 sites range from 1 megawatts of power generation at its smallest site and 15 megawatts at its largest site. The megawatt hours varies per year at each site. It would be useful to get an average range of energy generation per year for a solar array for our simulation to produce a more accurate or standard array before applying degradation during the simulation. The data selected was over the span of 1 year, looking for factors such as energy generated by two of the JEA inverters, irradiance of the solar arrays, the solar cell temperatures, the expected performances, and the temperature correction for the panels. We converted the yearly data from the JEA source into a spreadsheet. We prepared this spreadsheet for MATLAB manipulation by filtering through relevant data. Relevant data is important because it can show correlations between daily night-day cycles, seasonal weather patterns, and the cell's temperatures. This can help us understand efficiency ranges between JEA's expected cell performances and actual performances throughout the year. These factors will contribute to degradation patterns for the array simulation. JEA data was imported into MATLAB in tabular form. We can then manipulate the data by using commands such as stacked plot to replicate the graphs from the JEA source, or converting out of tabular form to isolate variables such as total energy generation or the energy generated from the inverter 1 or inverter 2. into things such as a 1 by 366 array or whatever size we would like. Then we can take means of the yearly data to make control measurements of solar energy generation or the degradation effects. We're currently working on a code to implement these variables so that instead of randomly generating the degradation effects in the simulation, we can use real-world data of the solar array conditions over the year that affect the arrays in the simulation in MATLAB. MATLAB can then indicate the arrays that are losing performance over time.
MATLAB was used to create a 20 by 20 matrix with random numbers. These numbers range between 0 and 400 watts. The numbers in this array represent individual solar panels in a solar farm. The location of the values within the matrix represent physical locations within a solar farm. The wattage values are separated into 3 different operating conditions. The values between 250 and 400 watts, the solar panel is given the value of 3. Values between 75 and 250 watts are given the value of 2. Last, any value below 75 watts is given a value of 1. The values assigned in the previous step correspond to colors that will be displayed on a 2D array. Any value with an assigned value of 3 will be green. The panels are in good working condition. Any value with 2 will be yellow. These panels need attention to increase the performance, but they are less critical. And last, any value of 1 will be red. These solar panels require immediate attention. The output of these panels are nearly 0 watts and require the most attention. In conclusion, the benefits of this software are vast. It makes it easier to determine where the problem solar panels are located. Technicians are able to quickly determine which solar panels have the lowest output and can prioritize the repair of the damaged solar panels. The reduced downtime will lead to a greater power generation, which can increase profitability.